In this video, we're going to explain this simple proposition that says if you have H to be a subgroup of G, and you have two elements A1 and A2 in G, then these two left cosets A1H and A2H, they're equal if and only if A1 inverse 8 times A2 is an element of H. Now, what this means in particular is just because A1H equals A2H, that does not imply A1 equals A2. What it does imply is that A1 is A2 times some element of H. That element H could be the identity element, in which case, yes, A1 equals A2, but it might not be the identity element. And then also A2 is equal to A1 times H prime for some H and H primed in H. Let's do an example before jumping into the proof. So let's take our group to be the integers with addition, H to be the subgroup of multiples of 10, and A1 to be 2 and A2 to be negative 8. Then these two cosets, 2 plus 10z and negative 8 plus 10z, are equal, even though the numbers 2 and negative 8 are certainly not equal. And if you ask what are the underlying sets of these cosets, well, 2 plus 10z is the multiples, the numbers that are 2 more than a multiple of 10. And so, for example, 2, 12, 22, but then you have to also go into the negative numbers, and 2 minus 10 is negative 8, and so forth. And then, negative 8 plus 10z is exactly the same set. And then, as an illustration of this condition here, again, we're using additive notation, and so this multiplication and this inverse, they turn into addition and subtraction. Also, A1 times H, that corresponds to, the times corresponds to plus down here. Okay, and then we check that A1 inverse A2, or in this case, negative A1 plus A2, turns out to be negative 10, which is an element of H, thus illustrating this condition here. Now let's discuss the proof of this proposition. So this proposition is an if and only if statement. So there's two directions we need to prove. So first, suppose A1 times H equals A2 times H, that these left cosets are equal. And what we want to show is that A1 inverse times A2 is an element of H. Okay, so A2 times the identity element, that's certainly in this left coset A2H, since the identity element is an H. And what we're assuming is that this left coset A2H equals this left coset A1H. So what we conclude is that A2 times the identity element, which is just A2, is an element of A1H. So that means that A2 times the identity element equals A1 times lowercase h for some h in H, and then multiplying both sides by A1 inverse, we get A1 inverse times A2 equals H, and so therefore we are done with that direction of the proof. So conversely, now assume that A1 inverse A2 is an element of H, and we want to show that these two left cosets, A1H and A2H, are equal. And so these are sets, and to show two sets are equal, it's typical to show one is a subset of the other and vice versa. Now our hypothesis or assumption that A1 inverse A2 is an H, if I multiply both sides on the left by A1, I get that A2 is an element of A1 times H, and so this coset A2H, well, that's an element, a subset of A1H times H. H times H is a subset of H. In fact, it's actually equal to H, since H is a subgroup. But anyway, we get A2H is a subset of A1H. Okay, so we've got this inclusion here. What we still need is this inclusion. And there, we use this fact that H is a subgroup, and so it's closed under inverses. And since we're assuming A1 inverse A2 is an H, that means the inverse of this element is also in H. The inverse of that element is written here, and using the rule for inverses of a product, we get that the inverse of this is you take A2 inverse, and that's written first, and then A1 inverse inverse, which is just A1. So we've got this element is in H, and so therefore A1 is is an element of A2 times H. And then going back to what we want to show, we start with A1H. We know that A1 is in A2H, and therefore, since H times H is a subset of H, we get that A1H is a subset of A2H, which is what we wanted to show.